methane exchange by tree stems. I'm going to talk about methane and carbon dioxide fluxes at the BIFoR phase, which is perhaps even more interesting. So just very basically, trees can emit carbon dioxide through the stems because all the living tissues in the stem respire, so they produce carbon dioxide, and part of that carbon dioxide is transported through the wood to the atmosphere. But also we know that part of the carbon dioxide produced in the soil through soil respiration, which means fine roots, mycorrhiza, other fungus, or heterotrophic respiration, part of that carbon dioxide produced in the soil could be transported through the roots and the stem and then emitted by the gasification of the stem. With methane, something kind of similar happened. Methane could be produced. So we know that trees can emit methane and exchange methane with the atmosphere through the stem. We know that part of that methane could be produced inside of the stem by methanogenic archaea inhabiting the stem, but also, particularly in wetland places and floodplains, methane could be produced in soil and then transported through the roots and emitted to the atmosphere by the gasification. But for methane, it's a bit more complicated because we know that the stems can emit methane, but also can uptake methane. So what we are measuring with the chambers directly in the field is not production or consumption, but is the net balance between both processes, which makes our understanding of the processes a bit more complicated, and also the modeling, it's a bit more complicated because, yeah. So I'm going to talk about carbon dioxide and methane fluxes from upland forests. And here, where I talk about, well, when I talk upland, it means places that soil has enough oxygen, so no wetlands, no floodplains. And very basic, we know that tree stems can emit carbon dioxide and can emit methane. We know that both gases show temporal pattern. That's very clear for carbon dioxide. So emissions increasing during the growing season and then decreasing after that. And there are few studies that also are reporting temporal patterns of methane stem fluxes. And as I said, we know that the origin of carbon dioxide and methane could be soil or could be the hardwood and the sapwood of the trees. And the magnitudes, carbon dioxide magnitudes are very variable, but methane fluxes are even more variable. So we can have uptake, we can have emissions, and even with the same tree, within the same tree, with few centimeters of difference, we can move orders of magnitude from uptake to emissions. So the goal of my experiment at BIFoR phase was understanding how the emission, the temporal patterns, the origin, and the magnitudes could change under elevated CO2 conditions. So the hypothesis here was, okay, if we have elevated CO2, then we may have higher photosynthesis rates. If we have more photosynthesis, then we may have more rise of deposition and non-structural carbohydrates, which may spin up the carbon cycle. So we may have higher carbon dioxide and methane fluxes from tree stems. On the other hand, if we have elevated CO2, then we may have an increase of water use efficiency, at least at leaf level. So that potentially could reduce the transpiration. So we could have more soil water, higher moisture in soil. If we have more water in soil, the levels of oxygen potentially are going to be lower. And if we have less oxygen, less respiration, so less carbon dioxide fluxes. And also, if we have low oxygen in soil, then we may have higher methanogenesis activity, so potentially higher methane fluxes. Those hypotheses are not really, they're not the best ones in terms of our thinking of the future climate conditions. Because as you can see in both cases, we may have higher methane fluxes from the tree stems. And you know that methane is much, much powerful greenhouse gas than even carbon dioxide. And depending on the hypothesis, we may have higher or lower carbon dioxide fluxes. So I studied stem fluxes at the BIFoR phase. You know, mature oak forest, we have 6 arrays, 3 ambient, 3 elevated CO2. And we were performing monthly campaigns. So we selected 13 trees, mature oaks, 5 per array, and we were measuring stem fluxes at 70 centimeters from the ground using a portable greenhouse gas analyzer, 6 minutes each measurement. But on top of that, we performed seasonal campaigns. So 4 times a year, we were measuring a subset of those trees at 5 different stem heights, from 70 centimeters up to 4 meters high. So basic results, yes, those trees are emitting carbon dioxide through the stems. The average rate during the whole year was 0.76 micromoles meters squared per second. And if we see the annual variability of CO2 fluxes, we can see a clear annual variability with emissions being really low during winter time and then increasing during the growing season and decreasing towards the end of the year. In all the slides you are going to see in this green, it's ambient CO2, in the orange is elevated CO2. What is interesting here is that we performed a mixed effect model and we didn't see clear differences between ambient or elevated. The data is the final data, but the analysis are still preliminary because the model that I ran didn't fit the assumptions of the model of normality, heteroscedasticity. So, but if you see the data, it seems that for every single month, carbon dioxide fluxes under ambient conditions are always higher than under elevated, except for 1 month, October. For all the other ones, emissions under ambient conditions are higher than under elevated, which is very promising. And then there is not a lot of data to compare that because studying elevated CO2 in a mature forest, you know, there are few places that you can study that. But there was a paper published by Roberto Salomon a few years ago from the EUC phase, and they show kind of a similar trend. In that case, was not significant, but also from the 3 campaigns that they did, the absolute values were higher always under ambient than under elevated. So it looks like the similar trend, despite was not significant. When we check the vertical profile of carbon dioxide fluxes, we didn't see a lot, so no difference between ambient or elevated, mostly because there were not vertical pattern with the fluxes from winter time to spring, summer, and fall. What about methane? When we put all the data together, the mean methane flux was not different from 0. And if we can see the annual variability of methane fluxes, there is no seasonal trend. It doesn't look, yes, we have some points with net emissions. We have some points with net uptake, but on average, there is no seasonal pattern. And because there is no seasonal pattern, of course, no difference between elevated or ambient. And with the vertical axis, it happens more or less the same. If you don't have methane emissions, you don't have vertical pattern and no differences between elevated or ambient. So coming back again to the hypothesis, it looked like that for the carbon dioxide, we may have less emissions under elevated conditions. So that means that probably that hypothesis that elevated CO2 is leading an increase in water use efficiency, so less transpiration, more soil water content, less oxygen, that may result in less carbon dioxide. It seems that this could be the path that our emissions are following. The good thing is that I'm not the only person working at BIFoR. We have other people measuring water use efficiency, other people measuring transpiration, soil water content. So yeah, that could be a piece of a much bigger puzzle. So potentially we may be able to see that there is a decrease on carbon dioxide emissions, but we have also the data for understanding why we have that decrease. And just like a conclusion, for me, there are a couple of things. At the first glance, when I saw, no significant results, damn it, I wanted positive results. It's going to be easier to publish. But to be honest, that's a very good result, because that means that under future conditions with more carbon dioxide in the atmosphere, trees are not going to emit more carbon dioxide. In the best case scenario, they're going to emit less carbon dioxide through the stems, which is good, and also methane. And that's important because most of the first paper published talking about methane emissions in upland forests show positive fluxes. And since that was 6 or 7 years ago, since then, several papers came reporting fluxes and emissions in upland forests. So everybody is assuming that the trees, all the trees in all the different ecosystems, they are emitting methane. What I'm maybe showing here is that there is a total bias towards positive results. So several trees or several species, at least in certain occasions, for instance, here, holm oak, I'm Mediterranean guy. Here, oak, are not emitting methane, which is also a good result. So yeah, that's it. Many thanks, especially Ecological Continuity Trust, for supporting this research, and many thanks all of you for your attention.
Well, thank you, Josep, for this amazing explanation. I really enjoyed the talk. And now we are going with the last speaker of the session, that is Emma Bass. She's from the University of Stirling in Scotland, and she's joining online.